Hello dear friends, welcome to the lecture of real analysis. We are studying complete metric spaces. And in this lecture we shall study contraction of mapping and fixed point theorem. So first we shall define what is a contraction of mapping, and then we will see example of it. After that we will write the fixed point theorem and prove it. Now before considering the definition of contraction, we will write a notation that we are going to use in the definition and also in fixed point theorem. Let T be a mapping from M to M. So we write, and suppose X belongs to M. So we write Tx instead of T of X. Generally we write the image of X as f of X, and here the function is T. Instead of T of X we simply write Tx. So this means image of X under T, that is actually T of X. Also, or you may write and T square instead of. This is brief notation we are going to use, T not T. Composition of T with T is to be written as T square, T cube instead of T square not T, etc. So this is the only two things that we have to note. Tx means T of X, T square means composition of T with T and higher powers are considered. Now we will write the definition of contraction. Let M with row be a metric space. A mapping T from M to M. Is said to be a contraction on M if there is a real number alpha such that, or you may write here as such that 0 is less than or equal to strictly less than 1, and row of Tx and Ty is less than or equal to alpha times row of x, y, and this happens for x, y belongs to M. Every x, y belongs to M. So this is the definition of contraction. A mapping from metric space M to itself, and is contraction if there is a real number alpha between 0 and 1 but strictly less than 1, and row of Tx and Ty. That means the row means distance between Tx and Ty. What is Tx? Tx means T of X is less than or equal to alpha times row of x and y. Alpha is less than 1, and this means that the distance between the images is less than or equal to the distance between the pre-images, and that means the mapping reduces the distance between the images, and therefore it is called contraction. So this is contraction on M. Now we will see a simple example for this. Here one thing is to be noted, alpha is independent of x and y, and a mapping which is defined as a T is continuous on M. Let M be the real number R1. M is equal to R1, and let T from R1 to R1 defined by T of x is equal to half x. X belongs to R1. Then this is a contraction that we will see. It is a contraction on real numbers. See, we can verify this. Now, what is row of tx and ty? This means row of, what is the tx? T of x is tx, and it is half x, and therefore, so we will consider here xy belongs to R1. Xy belongs to R1, and then row of tx and ty is equal to row of tx is half x and ty is half y. And further, what is the row? Row for R1 is absolute value metric, and that we know it is absolute difference of these two, and that is x by 2 minus y by 2, absolute difference of x by 2 minus y by 2. And by property of absolute value function, this half can be written outside this into absolute value of x minus y, or this is now mod of x minus y, or absolute value of x minus y is row of x and y, that is half of row of x and y. Now you see that this is a contraction, this becomes a contraction where alpha can be taken as 1/2. You see, row of tx and ty, equality is allowed there, and therefore equal to, we can take alpha as half, then this satisfies. Row of tx and ty is equal to half row of x and y. So this is a contraction, thus T is a contraction. T is a contraction on R1 with alpha is equal to, or alpha may be taken as, with one value of alpha is equal to half, and that is certainly between 0 and 1. So this is the meaning. And that why it is called contraction, because it reduces the distance between the images. And we may see this as, suppose if this is R1 and mapping is from R1 to RT. If this is X, then its image is half X, and Y, its image is half. So therefore the images will be like this. It is half x and this is half. So distance between x by 2 and y by 2 is certainly less than or equal to distance between x and y, because these are real numbers, and thus the image is contraction. It contracts the distance between the images. So that's why this mapping is known as contraction. Now we shall consider fixed point theorem, or which is also known as Picard's fixed point theorem. Further example of contraction we shall consider in exercises. And this is our next theorem. Theorem in serial order, which will be 4 or 5. So I think theorem number 5 you may verify. And let M row be a metric space, M with row be a metric space, and T be a contraction on M. Then see, this is the statement of Picard's fixed point theorem, and fixed point theorems are important in analysis. Also, these are applicable in differential equations, and they give the existence of solution for differential equations. And what is the meaning of fixed point theorem and why it is called so, fixed point? Because it is a mapping, contraction. Mapping is contraction, and just we have defined. And there exists one and only one point in the metric space M, such that T of x is equal to x, and that means image of x is equal to x itself. So yeah, in the earlier example we have T from R1 to R1 defined by T of x is equal to half x. Now what will be that point? How many points will be there here? Fixed point. And image must be equal to the same. So this must be equal to x then. So what this implies, half x is equal to x, means this is only possible when x is equal to 0. So 0 is a fixed point of this because T of 0 is equal to 0 and none other elements. That means this there exists one and only one point x such that the T image of that point is equal to itself. And here for this mapping or this contraction, T image of 0 is equal to 0. So therefore 0 is the fixed point for this contraction. Or the meaning of fixed point will be in real problems, the fixed point will be, see, if you consider a disc rotating or a fan, if this disc is rotating in clockwise or anti-clockwise sense, suppose it is rotating clockwise sense, and then every point of the disc rotates through in the sense of anti-clockwise direction, clockwise direction, and but one point does not move, and that point is the center. So center of this disc is a fixed point because the point does not move, all other points moves in this sense, and this is a real example of a fixed point theorem. And such fixed point are there in contraction, and that point is only one. So this we have to prove. Now for that purpose we suppose that this is in other words, that is T has precisely one fixed point. Precisely means exactly one fixed point. This is the meaning of the theorem, and the theorem is known as fixed point theorem. So we shall prove the theorem. So we will consider x and y belongs to M. Let x, y belongs to M. And by definition we have, since T is a contraction, and let T from M to M be a contraction. On M. So therefore we have rho of Tx and Ty is less than or equal to alpha times rho of x and y for some alpha 0 less than or equal to alpha is less than 1. This is by definition of contraction. And now further we will have, therefore, rho of say t square x, t square y. So what will be this? Yeah, we have written the notation for this. T square x means t of x, and that is composition of t with itself, and therefore this can be written as rho of t naught t of x and t naught t of y, or therefore this will be less than or equal to. Now if you consider this definition again, t of x, here alpha times rho of x and y. So this will be alpha times rho of tx and ty. The same definition we have applied here, and this t image of t of x, t image of t of y gives less than or equal to alpha rho of tx and ty. Again use the same, so this is further, that is less than or equal to, and this is alpha square rho of xy, using the same definition here. and thus we will have rho of t square x and t square y is less than or equal to alpha square rho of x and y. Also similarly, rho of t cube x and t cube y will be less than or equal to alpha cube rho of x and y. And in general, or n belongs to I, we will have rho of t power n x and t power n y will be less than or equal to alpha to the power n rho of x y, and we shall suppose this statement as 1. Further, we will consider the notation as let x naught belongs to m. Let x naught belongs to m, and further let x1 is equal to t image of x naught. We are using this notation, t image of x naught is equal to x1, and x2 is equal to t image of x1, and so on. We will have t image xn plus 1 will be t image of xn. See, t image of x naught is written with x1, means next suffix. x2 is t image of x1, x3 will be t image of x2, and xn plus 1 will be t image of xn, for n belongs to I. So this next, therefore we will have, see, t square. So this can be considered as t square x naught. x1 is equal to, or t square, or we will consider x2 is equal to. What will be x2? x2 is t x1, and t x1 is t of x naught. So x2 will be t square of x naught. We can verify here. What is x2? x2 is t x1, and what is x1? x1 is t x naught. So therefore t x1, that is x2. x2 becomes t square x naught. Similarly, x3 will be t cube x naught, and so on. What will be xn? xn will be t to the power n x naught. N belongs to positive integer. So this is what we have obtained. x1 is t of x naught, x2 is t square of x naught, x3 is t cube x naught, and so on. xn is t to the power n x naught. Now what we will show that this xn is a Cauchy sequence. We now show that we will show that xn is a Cauchy sequence. For that purpose, we have to use the definition of Cauchy sequence in metric, and we know that if we can prove rho of this is the result we will require further. We know that a sequence is a Cauchy sequence if rho of xn and xm is less than epsilon. Let n and m be positive integer. Let n, m belongs to R, and say m is greater than n, and if m is greater than n, that will be n plus some other positive number. So m is equal to n plus p. Therefore, what will be rho of xn and xm? This is equal to rho of xn, and what is xm? M is, we have assumed, n plus p. So m is greater than n, so it will be n plus certain positive integer. Suppose that n and m are say 7 and 10, then this 10 can be written as 7 plus 3. P will be 3, like this. So this will be xm means xn plus p. And now here we will apply the triangle inequality, and this can be written as less than or equal to rho of xn plus 1 plus rho of xn plus 1 xn plus 2 and plus so on. Rho of last is xn plus p, and therefore earlier to that will be one term less, one suffix less. That means xn plus p minus 1 and xn plus p. So this is by triangle inequality. Next, this can be written as, so this is less than or equal to. Now we will use this relation. What is xn? Xn is t power n x naught. That is less than or equal to rho of t power n of x naught. And what is actually xn plus 1? Xn plus 1 will also be written as t power n plus 1 of x naught. But we will write this as t power n of t of x naught, or that is t power n of x1. See, this is xn plus 1. Xn plus 1 in the same notation can be written like this, and thus we can write this as t power n x1. So what here to be noted is xn. This power and suffix, yes, power and suffix must be the number here, n. Here n plus 1 is n plus 1, the suffix of this number xn plus 1. And similarly, the next can be written as rho of t power n plus 1 x naught and t power n plus 1 x1. This one. And further, this is for written for your understanding. And now we can write directly this as plus so on. And last will be, this will be t power n plus p minus 1 at x naught of x naught. And but that next will be written in terms of x1. So each term is written in terms of image of x0 and x1. And you should note the powers. And that is t power n plus p minus 1 of x1. So thus we have this expression. And further we can now use by 1. What is here? It is 1. So now by 1 we have. Now what is the left side is the row of xn and xm. Row of xn and xm is less than or equal to. We have up to this step, and we will now write the next step to this. T power n of x naught and t power n of xn. So what is the row of t power n of x and t power n of y? That is less than or equal to alpha to the power n row of x and y. So using this, instead of x and y, here the numbers are x0 and x1. So that will be less than or equal to alpha power n. Alpha power n row of x0 and x1. In place of xy, here is x0, x1. And for the next, you see. So this is true for every n. True for n, n plus 1 and so on. So next we will be using the same alpha to the power n plus 1. T of x0, see row of, not t but row of x0, x1. And plus so on. The last one will be alpha to the power n plus p minus 1. Row of x0 and x1. So this is true for all n. N belongs to I. And now we can see here alpha to the power n is common. So therefore rho of xn and xm is less than or equal to alpha to the power n, and this also rho of x naught and x1. This is common in each, and what remains in bracket is, here it is 1, and next is alpha. Alpha to the power n is taken common, and that continues alpha square and so on up to alpha to the power p minus 1. So this is the right side, or therefore rho of xn and xm will be less than or equal to alpha to the power n and rho of x naught and x1. And this we can consider as a geometric series. And geometric series, if you consider this series as infinite, then its sum is 1 over 1 minus alpha. So we shall write it directly 1 upon 1 minus alpha. So this is less than, or that is actually less than, strictly less than. This is strictly less than this one. Since the reason here is 1 plus alpha square and so on, this sum is 1 upon 1 minus alpha. If 0 is less than or equal to alpha is less than 1. So this is or 0 strictly less than alpha, and that is less than 1. So it is true for 1 also, 0 also, and maybe written as the same. So thus this is the relation we have obtained, and now we have again alpha is less than 1. Therefore, what is the limit of this as n tends to infinity? Now, limit n tends to infinity of alpha power n. Here is alpha power n, and that is equal to 0, since 0 is less than alpha, the less than or equal to alpha is less than 1. This is a geometric sequence, and here if for geometric sequence a power n, if a is less than 1, between 0 and 1, then limit of an as n tends to infinity is 0. So we have studied this geometric sequence in the chapter of sequences. So that result is used. Means if you increase n, or if you take limit as n tends to infinity, this term becomes 0. And that means if you increase n and m, so this right side becomes smaller and smaller, because this is tending towards 0. So therefore, rho of xn and xm can be made arbitrarily small for taking n or sufficiently large value of n. As n tends to infinity means n becoming large and large, for sufficiently large values of n, and hence m. Because m is greater than n. If n is greater, then m becomes greater. So thus this is made arbitrarily small, means that means rho of xn and xm is less than epsilon for n m greater than or equal to n, or we can have and thus the same. Greater than or equal to certain number, and this shows that therefore xn is Cauchy sequence. This is the condition or definition of Cauchy sequence. Distance between nth and mth term is smaller and smaller, or can be made smaller, and therefore the sequence is Cauchy. And now we shall use the fact that m is complete. So thus we have proved it is a Cauchy sequence. Next, since m is complete, there is a number x belongs to M. There is x belongs to M. So what is the definition of complete metric space? Every Cauchy sequence converges to a point in M. And that's why we have first shown Xn is Cauchy sequence in M. These are the points in M we are considering. And therefore, M is complete means there is x belongs to M such that Xn converges to this x. Limit of Xn as n tends to infinity is equal to x. And because limit of Xn is x, therefore we will have limit n tends to infinity t of Xn is equal to t of x, taking t image on both sides. And this is because t is continuous, a contraction is continuous. So further we have t of Xn is equal to tx. But what is t of Xn in with earlier notation? T of Xn is equal to xn plus 1. We have written t of x0 is x1, t of x1 is x2, and therefore t of xn is xn plus 1. And therefore the sequence t of xn becomes xn plus 1, sequence xn plus 1, and is a subsequence. This is a subsequence of xn. Xn plus 1 we know is a subsequence of xn because its term starts with x2, x3, and its term starts with x1, x2, etc. So this is having one term more, and therefore this is a subsequence, is a subsequence of xn. And because it is convergent, converges to x, the subsequence must also converge to x. And must converge to x. Therefore, txn converges to x. Must also converge to x, because xn converges to x, and subsequence must also converge to x. And what that gives? Limit of txn as n tends to infinity is equal to x. Now you note these two. See what we have? Limit of xn is x. Here this is there. What is the limit of txn is tx, and what is here limit of txn is x. And thus what this shows, the left side is the same, and therefore their right side must be the same. Hence tx is equal to x, and therefore thus x is a fixed point. Fixed point, this is the condition for fixed point. Tx is equal to x, image is equal to the same, is a fixed point of M. Now what remains to prove is this point is one and only one. There is no other point with the same condition. So that we shall prove, then the proof will be completed. So it remains to prove that fixed point is only one. So further we will show uniqueness. Uniqueness of fixed point. Suppose there is y. Suppose on the contrary, there is y belongs to M such that ty is equal to y with the same condition. There is another point y which satisfies the condition of fixed point. Then what we will have, rho of tx and ty will be equal to rho of, now see ty is y, tx is x, so this will be rho of x and y. But before that, that is by definition of contraction, this will be less than or equal to, this is less than or equal to alpha times x and y. Yes, we will write this as alpha times x, y, and but this implies rho of, see what is tx is x and what is ty is y. This implies rho of x and y is less than or equal to alpha times rho of x and y. This is the definition of contraction. T is contraction, rho of tx and ty is less than or equal to alpha times rho of xy. And this tx is x, ty is y, left side is this one and right side is the same. So what this implies, dividing out by rho of xy. So this implies 1 is less than or equal to alpha. Since here there is a point y, another point y not equal to x. Since rho of x and y is not equal to 0. If these are different, by definition of metric, the distance is not 0. And if it is not 0, we can divide. And if you divide this, then 1 remains here and alpha remains. 1 is less than or equal to alpha. And this is a contraction. This is a contradiction. This is a contradiction. Or wrong result or absurd result. Why? Since we must have alpha between 0 and 1. 1 cannot be less than alpha. Alpha is strictly less than 1. Alpha and 1 is greater than alpha. Here 1 is less than or equal to alpha. And therefore, hence, x is unique. So there cannot be exist y. Hence, the point x is unique. And this proves the theorem. There exists only one point x. Or therefore there is precisely one and one point only, or hence the fixed point x is unique, and this proves the theorem. So thus we have proved an important theorem, which is Picard's fixed point theorem, using the definition of contraction of a mapping or contraction mapping on metric spaces. So please go through the proof and try to understand the proof. Remaining part we will continue next time. Thank you.